This is everything I always wanted to know about cryptography, but never thought I would understand. I found out just yesterday that it used to be called crypto, and apparently to some people nowadays that means crypto coins, so I feel a bit old because it's about cryptography. In a way, cryptography is the underlying technology behind crypto coins, so you could also consider it a very low-level talk about crypto coins. So my name is Sasha. You may have seen me as this on Twitter. This image has its own long story. I work for a company called Dashcare, where we do a lot of high-end Python and Django developments. I'm also a committer on Django itself, which is the most popular open source web framework. I do a lot of work around inclusivity and community, and I also organize several events. And so when I started getting interested in cryptography, I would constantly encounter things like this. And it's like, only half of the words on this slide make sense to me. I am very poor at mathematics. And so to me, it always seemed whenever I read anything about crypto or tried to understand anything, it was like trying to figure this out. But over the last few years, I've been finding better resources that work better for me in learning how these things work, and found that it's actually really interesting. And once you start understanding how a bunch of these parts work, a lot of other things fall into place much easier. I still don't understand everything. Also, this talk is not actually everything that I learned about crypto, because I only have one talk slot. They wouldn't give me two. So let's start with something. I mentioned I do a lot of inclusivity work, and not everyone likes it when I do that. So sometimes people try to insult me on the internet, and the best way they've done that is this. But it's encrypted. We can't read it. And but this is encrypted using a very poor cipher. So look at this text, and I've told you it's an insult. We can assume it's in English. What are some things you notice here? Are there patterns in the data? There's 2 apostrophes here, and they repeat. And so if you look at the structure of when people try to insult you, it's usually multiple long words. So we could assume that the apostrophes indicate different words. You can also see 2 words ending in the same letters in F and K, which is also a structure that we have a lot in natural language. And so for this example, I used a single byte XOR cipher, and what that means is that you take every byte and you XOR it with a key. And then you do that for every single one of them. And then out you get the most creative way someone's insulted me on the internet. This is a terrible cipher. This is a horrible idea. I'll show you what things it fails on in a moment. But in a way, it's even modern ciphers use sort of slightly like this in the basis, but a lot better. You'll see XOR operations, bitwise XOR operations used a lot in cryptography because they have certain interesting properties. And so the way this works on, say, the first character is that in ASCII, there are these bits. That's the top one. Then this is the key that I've used, which is the same for every character. And then you get the outcome. And basically, an XOR looks at every bit and says, is it different? So the first bit, not different. Second bit, they're different. Third bit, they're also different. And you see this often still in even ciphers that are actually good ideas. XOR also has the interesting property that you can move any of the operands around. So if you XOR the ciphertext with the key, you get the clear text. If you do it the other way around, you encrypt it. If you XOR the ciphertext, the encrypted text, and the clear text, you get the key. That's very bad. So what are some essential properties that this all fails on that you need to have? For one, your security cannot depend on keeping your algorithm or its parameters secret. It has to be about secrecy of the key. If it's secure only because you've told nobody which algorithm you're using, that is not secure. Also, the outcome, the ciphertext that you produce, has to be as close as possible to random. And it can't provide any hint to the structure. So like in the previous example, you could see basically structures of the encrypted text were leaking through in the encrypted text, in the ciphertext. That is a bad practice, because it means you are leaking information, even though it's encrypted, even though it doesn't have the literal words. Also, if your clear text changes, the ciphertext, even if it changes slightly, the ciphertext should change dramatically. So this prevents you. Otherwise, if you have two texts that were encrypted, and only the first letter was changed, and in the output also only the first byte is changed, then you have information because you can determine the coherence, how similar are two ciphertexts, which is undesirable. Also, of course, if you have an encrypted text and the belonging clear text, you shouldn't be able to retrieve the key, which would then allow you to decrypt other things. It should which is also something where our algorithm fails. And basically, there should be no faster method than a full brute force attack. Basically, as soon as you can do it faster, you could call it broken. There's some leeway in this sometimes, but not a lot. This is also a bit simplified because we only have 40 minutes, so this goes for all of the talk. I am skipping a few things. Also, another one is, of course, a sufficiently large key space. So in my single byte XOR cipher, the key is a single byte. That's only 256 values. So you could work this out on paper. You could brute force it on paper by hand before this talk ends. So your key space needs to be sufficiently large. A more modern standard is the advanced encryption standards. This is very widely used. It is so common that your CPUs have native instructions to deal with this, which also makes it very fast. And so AES is a block cipher, which means you take 16 bytes of clear text information, and then there's an encryption function which gets a key of 128, 192, or 256 bits, and out comes 16 bytes of ciphertext. And you can decrypt, and it's basically the other way around. You can actually slightly recognize the earlier cipher I showed you in AES. So basically how AES works, you put the 16 bytes in a matrix, and then you substitute each value with a different one, which provides through the fixed set of substitution values. Then you take your matrix of data, and then you shift all of the rows by a certain amount. So top none, the next one you shift by one. And so you basically you remove the coherence between the different columns. And then in the next step of a round, you take each column, and you modify it into different values, also based on the translation. And then the last step is something which kind of looks like our earlier cipher, which is you take each byte in your matrix, you take a byte from a key that you generated, and you XOR them. AES does this 10 to 14 times. There's a few other details. Do not implement AES on your own based on these slides. But so basically, this key is basically generated each round differently from the actual key that you're providing. But through all those other steps, it basically loses the coherence between the clear text you put in and the ciphertext that comes out. It basically, so you can't reveal the structure that was in the original text. You can't reveal that in the ciphertext. And so a block cipher, AES is one of them. There are a bunch of others. It encrypts at a time precisely 16 bytes of clear text and produces exactly 16 bytes of ciphertext, which creates kind of a problem because often we want to encrypt more than 16 bytes. 16 bytes is not actually a lot of data. So what do? You can do something very naive. You take your first 16 bytes of clear text, you encrypt them, you produce 16 bytes of ciphertext. Then you take the next one and do exactly the same thing with the same key. This has a name. It's called Electronic Codebook. It is a terrible idea. Because it still reveals the structure in the data. If you use this on, say, this image, you get this output. So you can still see that a lot of the original structure of the data is still in there, which means you're doing a poor job. And this is because in these kind of images, if the same 16 bytes from this pixel here gets basically encrypted in the same way here as if it was this white pixel and here with some variation. So this definitely tells you something is not going right. If you just get static out of it, that doesn't mean you're doing it right. So this test only works one way. So there are better options. if you want to encrypt more than 16 bytes. One of them is cipher block chaining, very popular. And you start basically in the same way. And then before you encrypt a clear text, you XOR all the bytes with an initialization vector. That means an initialization vector is a random value which is not secret. And I'll show you later why you need a random value, even though it's not secret. Then for the next block, you take the ciphertext that came out, and you XOR that with the next clear text before you encrypt it. And then the ciphertext that comes out of that, you just do it to the next one, and so on until infinity, until you have all your data. And so what this means is that if these two clear text blocks were identical, they don't produce two identical ciphertexts. If they were different, they also produce different. So like whether or not these are the same or not doesn't reveal any structure in the original data. Another mode that's sort of like it is the counter mode. In counter mode, you don't directly encrypt your plaintext. You encrypt a nonce with a counter in it. A nonce is sort of like an initialization vector. It is random. It is not secret. And then you XOR it with the plaintext. And you do that every time. And because there's a counter and it's different every time, the same plaintext do not result in the same ciphertext. Counter mode and CBC mode have some up and downsides, each also around optimization, like whether you can parallelize encryption or decryption, so there's a performance choice there. And so why do you need a random nonce and a random IV, even though it's not secret? Because if you use the same one and you encrypt the same data, it's going to have the same results. So in fact, if you take two images that are only slightly different, then they will produce exactly, and if you XOR them, they will produce exactly the same output until the first difference. From then on, they're different. And this is because if you encrypt the same data with the same IV, you get the same ciphertext, which is then used for the next block, which then has the same outcome. In counter mode, this is actually worse. You'll be able to distinguish all the differences. So this is why people use random IVs. Otherwise, you can determine coherence between two messages. How similar are these messages, which is also a poor idea. So let's do a little example. This is Python, but it works pretty much the same in every language. We take a clear text for AES. We take a random key, and then you encrypt that. And so we're using ECB mode here, which generally is a bad idea, but we're only doing 16 bytes, so there's no difference. I can know the ciphertext. It reveals nothing. You can't figure out where the spaces are. This is something that AES is written for and very good at, even still after 17 years. And then you can decrypt it. And if you use the same key, oh, this is a typo on my slides. Instead of the AAA, we use the same key. I edited it later. So if you use the right key, then you get your answer back. What happens when you use the wrong key? Anyone want to guess? Sorry? Someone is onto this. When you use the wrong key, there's no such thing as errors in this. You just get a random string out of it. Because in the AES algorithm, I showed you it before, it's just a series of calculations. There is no right or wrong answer in a way. So, I mean, of course, you can't read the actual data because this is all nonsense and garbage. But there's no such thing as it failing with the wrong key. And you can abuse this in very interesting ways. For example, if you have a CBC decryption, this is sort of in the middle of the block, so we get the ciphertext of the previous block. So this is decryption, so we're going that way. So you take a ciphertext, you decrypt it with your AES function, and then you XOR it with the previous block. It's sort of upside down from the encryption. What happens when, say, you transmit this over a network, and I can intercept your ciphertext, but you have your encryption and decryption on different sites? Of course, I can't figure out your actual data from the ciphertext. But if I produce a variation in it, say I flip a bit here, then of course this block will decode to complete garbage because it's going to be decrypted with it's the same with the wrong key, or if you corrupt the ciphertext, it's just going to be pretty much random data. But in the next block, you produce a predictable variation in the clear text. So even though I've never had access to the key, and I've only been able to manipulate the ciphertext, you can trick a system into decrypting data that people sometimes assume is authentic because it's decrypted. But actually, you're producing predictable variations in it. Whether you can exploit this sort of depends on the situation. Like if there's, for example, this is some JSON, and that second block has something that says admin is 0, then you could use this way for privilege escalation. It also depends on, is it OK that that block is garbage? Maybe the parsing will fail because of that. So the exact situations where you can exploit this, like sometimes you can. There's a more interesting attack, which I'm not going to show you because it takes too long, which is a padding oracle. And it's basically related to this. It is pretty complicated to explain, but it basically comes down to that if you have a source that you can send this ciphertext to, and it'll tell you whether it decrypted correctly, you can, and you basically build it in this way, you can decrypt an entire message by playing with these kind of manipulations. You can basically retrieve enough information to decrypt an entire message. And basically the problem here is that you've encrypted the data. It is confidential. Nobody else can see what's in it. But you have not authenticated it. You don't know whether the source you got it from, whether you actually got it from the source that you trust. So that brings us to hashing and authentication. Cryptographic hashing, I'm sure it's something many of you have used. You take a word, you hash it. In this case, SHA-224, a hash comes out. If you change it slightly, a completely different text comes out. Or if you make it shorter. And so cryptographic hashes basically, they also have a number of properties that are desirable. For one, it has to be fast and not require a lot of resources. There is a catch to that in some cases. When you use a key derivation function, you want a variant of this where it's slow. But in basic hashing, you want it to be fast. When you see a hash, it shouldn't be possible to calculate what you hashed, to backtrack that without trying every possible input. Hence why it's unfeasible, but not impossible. If you change the input slightly, it should change the output dramatically. So if you see two hashes, you shouldn't be able to figure out how similar the inputs were. Of course, if you give it the same data, it still always produces the same hash. And you shouldn't be easily able to find two messages with the same hash. So if somebody's expecting a hash, I shouldn't be able to craft a different message that produces the same hash. Technically, you can, but you'd have to try every possible value. So not impossible, it's infeasible. This is something we call collisions. This is sometimes cause of confusion because collisions will happen in hashing. There are two messages that will produce the same hash because there's only so many bits in a hash. It can't have a unique value for every possible input. The trick is that you can't find them easily. So naively sometimes then say, oh, we need to do hashing because we need to authenticate the message. And they basically take AES CBC encryption. You put in a key initialization vector, the IV being random but not secret, the key is secret, produce the ciphertext, then you hash the ciphertext and you put that all in a message. The IV needs to be part of what you're sending because you need it to decrypt. This adds zero security because if I want to change the message, I can just update the hash as well. Because I change the ciphertext, I generate a new hash, I give it to your system and you say, it's authentic. So something that you use for this is a hash message authentication code, which basically makes use of a cryptographic hash like SHA-2, but also a key. And it basically means that you always, first of all, you take the IV and the ciphertext together for your hash. Otherwise, there are still attacks. And this basically means that when I try to tamper with this message, I cannot generate a new valid hash because I don't have your key. This is one option that people do. There are also variations where you do the HMAC before you encrypt. There are some up and downsides to each option. This is one of the most commonly used ones. Another option that's nice is GCM mode, which sort of looks like counter. If you look in the top, you see there's a counter 0, it increments, counter 1, encrypts, then XORs with a plaintext to produce ciphertext. So in the base, it's counter mode, but with a number of additional steps where it also produces an authentication tag. And this base which you're providing and when you decrypt it. So this is a block cipher mode, which embeds the authentication already, which is nice because the less you have to do, the less there is for you to screw up. So yeah, GCM is somewhat newer, so not everything supports it yet. And so what we've been talking about now are symmetric ciphers. So we use the same key for encryption and decryption. Symmetric ciphers are nice. They're very simple. Like I showed you some slides. That basically is the fundament of AES. They're incredibly fast because they're just a bunch of basic calculations. But the downside is, of course, you have the same key. So how do you deal with transferring the key? Like if somebody visits a website, you don't want to negotiate a key exchange with them by hand before. You don't want to mail them or send them a key by post for symmetric ciphers. So they're very nice, very fast, but they don't always practically work so easily. And so we also have asymmetric ciphers, which use different keys for encryption and decryption. Asymmetric ciphers are a lot more complicated. But the fundament of them is usually that they involve some kind of trapdoor function. It is some kind of mathematical problem that going from one value, one way to the other way is very easy for a computer. But going the other way is incredibly hard unless you have some additional data. So how does it work? Let's say in RSA. RSA is one of the most common asymmetric ciphers used extremely widely. You take a clear text, you encrypt it, and you need to have a public key of the person you're sending it to. The public key is public. It doesn't help you with decrypting data, so you can just share it everywhere, and that's safe. Then you can send it over an untrusted channel, say the internet, and then only with the private key you can decrypt it. For RSA, the trapdoor function is basically based around prime vectorization, which means that if you multiply very large prime numbers, that's very cheap, very easy for computers, not for humans. But distinguishing what the original factors were once you have only the outcome, that's really hard. That's sort of the essential mathematical problem behind RSA. Because of the different nature in which it works, RSA keys are typically bigger. So a 256-bit key for an RSA encryption would be laughable. With RSA, people generally use 2048 to 4096-bit keys because they're also not just any random data is a valid key. In AES, any 256-bit value is valid. It's also very slow comparatively. So, and that's not great because we want things to be fast. Websites need to load fast. And so something people often do in a way is to basically the clear text that they exchange, they then use as a key for AES. So you use a asymmetric encryption like RSA to securely send a key to the other party. Then you both have the same secret. You have a shared secret. And then you can do a symmetric cipher using that shared key, which is nice because it's fast. This is slightly simplified. SSL actually does this in a bunch of cases, but they have a few more steps involved. There's a downside, which is why this is not so popular anymore. We're going to assume that the actual communication channel between these two people is potentially compromised. Could be the internet, could be Wi-Fi. And so we're going to have to assume that other people can intercept that data, which is why we're doing crypto in the first place. However, something very interesting happens when you obtain this data and store it for a while, like maybe as part of a dragnet or because, you store a lot of the data that goes through your network. And then a year later, this private key is compromised. Then you can use it to decrypt this communication channel, which then provides you all the shared secrets for that communication channel. And so even if you obtain the private key later, you can decrypt all the secret data that was exchanged in the past. This is not ideal, something you want to avoid. Another interesting method is, which in some cases prevents this, is a Diffie-Hellman key exchange. It's very interesting. I will also not show you in detail how it works because I still don't fully understand it. In this case, you both have a public and private key. You have the other person's public key and your own private key. Together with a bunch of random data, the algorithm basically does a bunch of work. Then you exchange each other's work. Then you do some more work. And then you end up with the same shared secret without it ever having been transmitted over the wire and without the communication between the two of you ever having contained enough information to find the key. So even though you have a completely untrusted communication channel, you both end up on the same shared secret. Diffie-Hellman is not encryption, so whereas RSA can encrypt, Diffie-Hellman cannot. It only produces the shared secret for you, and then you can use whatever, AES probably, to actually do the encrypted communication. So Diffie-Hellman can solve this problem that we saw before with private key capture. And not having that problem is called forward secrecy. Forward secrecy is that if in the future your private keys are obtained, the communication you had up to that point is safe. This sort of depends on your exact implementation. So in case of SSL, you usually distinguish something that's called DH, which reuses a bunch of the parameters, which basically means it does have the same problem. Private key capture does lead to compromise of communication. You can also use ephemeral Diffie-Hellman, called EDH or DHE, where you use different parameters every time, and then you do not have this problem. So if you later, your private key and your communication were compromised, your data was still secret. The downside of this is that it's really slow. It's really, really, really slow, which is why one of the reasons it was never so popular. Up until some years ago, forward secrecy was also not considered that important, but some revelations have made it more of interest to people. So yeah, slowness is a bit of a problem, but there's something else that's very cool, which is called elliptic curve cryptography. That might be called, in Diffie-Hellman, we would call it ECDHE often. And so how does it work? I don't fully understand. It's like, it is a whole level more complicated than RSA. Basically, it uses a different kind of complex mathematical problem around paths that follow around elliptic curves. I don't think I will actually understand this in my life. But the most important part is, it is much, much faster. It can use smaller keys also. And so the performance of this is much, much better. I don't know where there's a black slide. There's still another problem, which is trust. So let's say we take an exchange of information. So there's a public key, and you want to exchange messages. So one of you has a public key. Then you send the public key. You do an RSA encryption. You have a message that's encrypted, and then you send it back. This sort of works, but there is a risk. So the message might be a shared key that you then use for symmetric encryption or anything else. There's a risk, which is if there's a party in the middle, then they can intercept the communication, and instead of sending on the right public key, they can actually send their own public key. The message will be encrypted with the person who's intercepting with their public key. They can then decrypt it. They can re-encrypt it for the actual destination. They can change the message in between, and nobody actually knows. This is, yeah, so even though you're using fancy RSA, even though you're using all the right, even though your encryption is solid, this still means it's essentially useless. If you cannot validate whether the key you get here is authentic and whether it's the right key, then the whole thing is academic. Not entirely. It's still better than having no encryption at all, because the attacks become slightly more complicated. And so for that, one of the most widely used methods is having certificate authorities that sign certificates. So let's say I want to do this for my domain name. I bet a lot of us have gone through this. You take my public key, and then a certificate authority will sign this, another feature that RSA has. And then we get a certificate, which has my public key and a signature from the certificate authority that says, this is solid, this is the real certificate. And the reason they can do that is they do some kind of check whether I'm actually allowed to do this. And they have all sorts of rules about this. Sometimes they violate them. Sometimes the certificate authority gets completely compromised, and then some people have a very bad day. Usually this works through a chain. So, in your browser, you have a list of trusted certificates. These are all people that promise to only give certificates in certain circumstances. Usually there's some intermediate certificate, and so you get a chain of trust, a cryptographic chain, which you can verify, that shows that I am the actual legitimate holder of that domain name. So I'm supposed to have a certificate for that according to these people, which Google has chosen to trust. The whole system around this is called public key infrastructure. So that's like also the whole process side of it. These people have like all sorts of committees in which they meet and make decisions, like when can you revoke a certificate. Certificate revocation is a bit messy. This is one option. This is something we use for many applications, like basically websites, lots of mail, things like that. Another option you may have seen is Web of Trust. PGP does this, for example. It's theoretically nice, but it's hard to scale. It has a lot of problems. It's also a bit more anarchistic, so this, of course, depends on the certificate authorities and our trust in them, and sometimes they'll do bad things. Some of them are governments. They might do bad things. Yeah, it's not all ideal, but it works for a lot of cases and prevents a lot of these attacks. So because someone else is not supposed to be able to get a certificate for my domain, and so the browser shouldn't trust it. So one of the most common applications that we all use, like literally right now, of course, is SSL, or as it should actually be called, TLS. Nobody actually does this correctly, so I've sort of given up. The basic history is like SSL v1 was never actually published. SSL version 2 was absolutely horrible. And so in SSL version 3, only a year later, it was completely redesigned. Version 3 is now also obsolete. TLS 1.0, the name was changed to Transport Layer Security. It has like sort of minor differences. 1.1 added hardening. 1.2 added very interesting authenticated encryption. So the GCM mode I showed you before, where you have the block cipher mode, includes the authentication, is supported in TLS 1.2. Also, you can do extensions. And just came out TLS 1.3, which actually mandates forward secrecy. So you can't do cipher suites without forward secrecy. And authenticated encryption. And there's a bunch of other security hardening it. So this is really solid 10 years later. TLS itself doesn't define which ciphers you should use, whether you should use AES or RSA or whatever. Within certain boundaries, like there are some requirements, especially in newer versions. And so it works with cipher suites, where you basically put all these parts together. So you could have TLS RSA with AES 128 CBC SHA, which basically means it's TLS. It uses RSA key exchange, which is basically the thing I showed you before. You send a shared secret to someone, and if they're able to decrypt it, you can use that for a symmetric communication channel. So, it's very basic. It does not offer forward secrecy. It uses RSA for authentication. This is almost universal, so it uses the public key infrastructure to figure out, do I have a chain of signatures that leads back to someone that I trust? It uses SHA-1 for the message authentication code, so for protecting against tampering. SHA-1 is not a good choice for anything, really. More modern ones, you could have TLS, ECDHC, RSA with AES 128, GCM, SHA-256. This is something that TLS 1.3 would allow. So this is elliptic curve, ephemeral, Diffie-Hellman key exchange, which means you get forward secrecy and it's fast. Very good. It still uses RSA for authentication. It uses AES 128 in GCM mode and a SHA-256 pseudo-random function. I'm going to skip explaining that because we don't have a lot of time. It's not super interesting. Especially older versions of TLS, there was still a lot of horrible cipher stuff. So TLS doesn't necessarily mean safe. TLS-TH anon export with RC440 MD5, which basically means it uses Diffie-Hellman key exchange, not ephemeral Diffie-Hellman, so there's no forward secrecy. It's anonymous, so there's no authentication. This is technically a thing SSL supports. RC4 encryption with 40 bits, MD5 MAC, both of which are absolutely horrendous options. Might as well not bother. You also notice it's flagged as export, because in early days of this, legislation around importing and exporting cryptography was still much stricter, so there were separate ciphers for exporting, which were weaker. Nowadays, this is easier. There's still some legislation, but it's at least not as strict as saying you can't export strong encryption from the United States. I'm presuming no modern browser would actually accept this, so both browsers and web servers. If you have a web server, you'll have to configure this. The defaults are not always great, but also browsers, they have a set of ciphers that they'll accept, and stuff like this, they are unlikely to accept today anymore. They'll just say, can't build an SSL connection that's remotely acceptable. So what should you do? For TLS configuration, I recommend this test. made by a company ironically named SSL Labs. As I said, I've given up on SSL versus TLS. They run a very, very extensive set of tests. There is so much in here. And basically, I, of course, score A+ on my own website. And yeah, so they check for like which ciphers do you have enabled, but also which browser is going to negotiate which cipher with you, and what are the good or bad properties about that. Checks for a lot of SSL vulnerabilities, whether you're breaking compatibility with certain things. I at some point had a security audit for a project I was running for a government, and in the report, they mentioned like, yeah, you're still supporting these old ciphers in your TLS configuration. And you should disable them because they're less secure. Because you only really need them if you're running IE7 on Windows XP. And so we had a meeting about it, and he asked me about it, and I said, well, IE7 on Windows XP, what do you think our national government runs on their desktops? It'll tell you about things like that. If you're breaking Windows XP compatibility, it'll warn you also. If you're going to do symmetric crypto in your own code, my first recommendation would be a thing called Fernet. I don't know whether that's how you pronounce it. It may be French. Fernet is nice because the screenshot I have is from a Python cryptography library. There are a bunch of other implementations. I think there's Go, there's Ruby. And it's nice because there's very little for you to do wrong. So it does a lot of things right already. This particular implementation does key rotation also. So if you want to change the key, it helps you deal with that. If you can't use that for some reason, I mean, like, it's hard to make a very specific recommendation for this. So AES-256 GCM is generally a very good choice, very solid, not supported everywhere. So if you need backwards compatibility, that can be an issue. I very briefly mentioned key derivation functions before. These are a bunch of them. If you're going to take user passwords and use them as a key, you need one of these. Fernet is actually not this. It is AES-128 CBC with a hash-matched authentication code. That's OK. It's not bad. But this option has less to screw up for you. If you're going to do asymmetric cryptography in your own code, yeah, it's a bit tricky. You could integrate with Cano PG. I've done this for an application. It's not very pretty. Cano PG is not a thing that likes to integrate with. If that doesn't work, then it's nearly impossible to give a specific advice. It really depends on how exactly you're seeing it, what your use cases are, to figure out what a good solution would be here. And that also sort of feeds into what are common errors that people make, and one of them is basically the failure to consider the wider ecosystem in which you use this. Because I can tell you, if you're going to do asymmetric crypto, use RSA with 4096-bit keys. Does that help for you? Does that make things safe? I don't really know, because I don't know enough about the rest of your ecosystem, your threats, what are acceptable risks, what are acceptable user usability impacts. So yeah, sometimes people use all the fancy new crypto, and it's very solid, and they have something else that's horribly insecure because all their users chose the password 123. Cryptographically secure, not very useful. Failure to authenticate a message authentication code, so not including it, not checking it when you decrypt, not checking your certificate chain, really common. And then it's, yeah, sort of useless. And generally confusing authentication and confidentiality. So if you encrypt something in itself, it makes it secret. It means other people can't read it. It doesn't mean when you read the data later, it's still authentic. That is a separate step. You can have authentication without confidentiality also. It's sometimes useful. Improper handling of the keys, so like taking user passwords, using them directly as an AES key, so not using a key derivation function, not storing your key securely. This is also a thing that feeds in 2.1, because you don't want to lose your key because you'll lose your data. But also, of course, if you publish your key, then yeah, if your key leaks, that's also not pretty. And then the last one are side channel vulnerabilities, that there's something else other than the core crypto thing you've done that is broken. So maybe the errors that you're providing to people, give them additional information about what's going on. Timing can give you additional information. Compression is an interesting one that has been coming up recently. So breach and crime came up like a few years ago. I don't have time to explain them. They are fascinating. You should read about them. It's basically where the compression of data in certain environments allows you to derive information about the encrypted content based on how big the output is. If you want to learn more about this, basically where I started, like figuring out like, oh, I can actually learn some of these things, was this set of crypto challenges. It's made by a company called Matasano. They do security, and these are a very interesting set of challenges. Every time they give you just enough information to learn something new, but they don't just give you the answer. So you really have to think, but they give you enough that you can work it out on your own. I never actually finished the whole set, but already I found like, I learned a lot. I felt more confident in that I could learn these things. I found actual real-world vulnerabilities, which were basically covered in like exercise 5. Also, I can't recommend this book enough. This is Bulletproof SSL and TLS. And so it's a very accessible book. It's not only about SSL and TLS, so it talks about lots of other considerations in cryptography, pretty much all the major vulnerabilities we've seen in the last years and how they work. Some of them are very ingenious. So yes, absolutely buy this book and read it. And that is all we have time for today. So I hope this is not the most practical cryptography talk. As I said, don't implement AES based on my slides. But I hope it's given you a bit of more insight of the underlying things. And once you know more about these things, then other things fall into place easier. And I hope it encourages you to also start doing these crypto challenges and do maybe the version 2 of this talk next year here. Thank you very much.